Okay, thank you, everybody. We're going to make a start. So slight interruption because the Zoom version of the conference wasn't working. So welcome, everybody. So again, Lucy is going to talk to us about non-compliance in survival data in cluster randomized trials. And in the short break, I learned that Lucy has only started working on this for 2 months. She's just out of her MSc. Welcome, Lucy. Thank you.
Thank you very much. Sorry for the wait. Thanks, guys. So yeah, my name's Lucy, and I'm an NIHR pre-doctoral fellow currently working at the University of Leicester. Despite what the title of my talk may kind of look like, this is actually just going to be kind of a really non-technical overview of the work that I carried out for my MSc dissertation this summer. So the motivation of this project originally came from a cluster randomized trial for a diabetes prevention program called Let's Prevent Diabetes. The intervention was a structured education program delivered over the course of 2 years in 3 education sessions. And the aim was to assess whether this intervention reduced the incidence of type 2 diabetes in individuals who were already at a high risk. So the data was originally analysed on an intention to treat basis, which, as I'm sure everyone knows, is generally the gold standard in most clinical trials because it provides us with the effect of offering a treatment or intervention. But there are some scenarios where we may wish to obtain the actual efficacy of an interventional treatment. In addition, non-compliance is known to reduce the power of an intention to treat analysis, and there was a fair amount in this trial, with 22% of participants not attending any of the education sessions and only 29% attending all 3. So a secondary analysis was conducted using a per protocol approach, and the results of that, which can be seen in this table, showed a sort of dose-response relationship between engagement in the intervention and the outcome of participants. So, for example, retainers who attended all 3 education sessions on average saw a greater reduction in incidence of type 2 diabetes than engagers who just attended the first session. However, while these are the kind of the results we would kind of hope to see, methods such as per protocol and as treated can be quite problematic because they obviously exclude groups of participants from the analysis, and by doing this, we're breaking randomization and inducing selection bias. And therefore, these results can only be taken to be kind of causal under the assumption of no unmeasured confounders. So despite this being an issue in a number of trials, and obviously in cluster trials, we actually have the potential for non-compliance to occur at both the subject and the cluster level, there's a distinct lack of guidance on how to deal with this. So the consult statement generally favours an intention to treat approach and advises ignoring any deviations from the protocol. I'm aware this is currently being updated, so it will be interesting to see if this advice changes at all. I'm obviously not saying that we shouldn't use intention to treat because, as I said in my previous slide, it's generally one of the most useful inferences. But there are plenty of existing methods that allow researchers to go beyond this and actually adjust for non-compliance within their analysis, if so desired, even if it's just as a secondary or exploratory analysis. So the aim of my study was to review a number of these existing methods and kind of initially apply them to the diabetes data. Just a quick disclaimer that this was in no way a formal kind of systematic review or anything, because mainly because of time constraints. But the 4 methods I did consider are listed here on this slide. In this presentation, I'm predominantly going to be focusing on the instrumental variables method, which uses treatment assignment as an instrument in order to estimate the causal effect of the intervention, assuming that all people assigned to it had complied. And then also the rank preserving structural failure time model, which uses a really similar idea to this, but in a much more survival specific setting. And for both of these methods, I just accounted for clustering by calculating robust standard errors. So I'm not going to go into any more detail about these methods here, but none of them are particularly novel. There is so much literature on them. And so if anyone's interested, I'd obviously be happy to direct you towards that, and it will be in the references as well. So this graph shows the results of applying each of these methods to the diabetes data set. It's probably not completely fair to compare these directly in this manner, because they do produce slightly different estimands. Hence my very vague labeling of the axes. But what this just really kind of simply shows is that under each method, there was a reduction in incidence of type 2 diabetes in the intervention group, but one that's not statistically significant. And this was the same conclusions made by the intention to treat analysis. However, just because in this case, using a different method and actually adjusting for non-compliance didn't give a different overall result, doesn't mean that this would be the case in all trials. And also, obviously, just applying these methods to one data set doesn't really tell us much about their performance. in general. So because of this, I then conducted a simulation study to further compare the instrumental variables method to the rank-preserving structural failure time model. I selected these two because from my initial analysis, they seemed to be the best suited to this clustered survival setting. So I considered a range of different scenarios in my simulation study. I looked at compliance status being both randomly generated and based on a covariate at the subject level. And for each of these, I considered a range of different probabilities of non-compliance. And then I also looked at varying the sample size and the ICC too. So just really briefly, some of the key things I found were that neither method performed particularly well at high levels of non-compliance. So as the probability of non-compliance increased, the bias of methods did as well, which is probably what you'd expect. And the instrumental variables method was actually quite biased in most of the scenarios. And this was really interesting because it sort of contradicts previous simulation studies that have been carried out with kind of a binary outcome that consider this method and perhaps suggest it's not particularly suited for a survival setting. Whereas the rank-preserving structural failure time model performed much better, which you'd kind of expect because it is, as I said, more set up for a survival setting. And I also found that varying the sample size in the ICC didn't really impact the performance of the methods. And this perhaps suggests that the way clustering was accounted for was kind of fairly robust. So in conclusion, based on this simulation study and kind of just the general project, I would advise consideration of a rank-preserving structural failure time model to adjust for non-compliance in a cluster trial with time to event outcome where you have kind of low to moderate levels of non-compliance. However, this does come with a couple of key considerations. So firstly, this method's predominantly been recommended for use in trials to deal with treatment switching. And because of this, it requires us to define the amount of time spent under the treatment by each participant. And this isn't always intuitive. So, especially if you're looking at an intervention, there's not always an obvious way to do this. However, in the kind of initial part of my project, I did look at defining this in a few different ways, and it didn't really seem to impact the overall results. But I do think this is something that should be further investigated. Also, as with all other methods, this model does obviously come with its own assumptions. And so anyone considering using it should obviously weigh these assumptions up against the assumption of no emergent confounders made by per protocol analysis or kind of any other methods they're considering using, and obviously decide on a case-by-case basis which is the most appropriate. Finally, while simulation studies are a really good way of assessing the performance methods and comparing methods, as I did in this project, they are subject to issues of external validity because they each consider, very specific settings. And because of this, I'm about to conduct a systematic review of all simulation studies of this nature, which kind of look at different methods to account for non-compliance. The aim of this is to assess which methods are most commonly used by researchers and hopefully produce some sort of guidance as to which is the most appropriate method to use in a range of settings, such as the clustered survival setting. Thank you so much for listening. I will try my best to answer any questions, and please feel free to contact me if you have any other kind of feedback or comments on this presentation. And also, if you scan this QR code, there's a list of references which are related to what I've been talking about. Thank you.
Thank you very much, Lucy. Any questions for Lucy? Sam? Oh, yeah, sorry.
Thanks, Lucy. I'm very impressed in what you've achieved in just 2 months. So, on the question of your IV estimate, you've got obviously a non-linear model and non-linear outcome here. What IV method did you use? Was it like a residual inclusion approach?
Yeah, so it's kind of a two-stage least squares regression, and the first stage kind of tries to predict the exposure based on the assignment of the treatment, and then the second stage, so that's just obviously like a logistic regression. And then the second stage uses I think I used a Cox model, but any survival model you could use, and then incorporates that kind of predicted exposure into that model. If that makes sense. Okay, yes, because I think the other way of doing it is you take the residual from the first stage and use that as an additional covariant. Yeah, I think that's what I did. Yeah. Oh, okay. Thank you.
That's a good question. Thanks for your presentation, Lucy. I may have missed this, but is this about non-compliance at the level of the subject or at the level of the cluster?
Well, I didn't really delve into that in any more detail. Kind of both, I guess. I guess here I'm assuming that there's not really a distinction between them. I think if I'd extended the simulation study, I would have kind of gone into that a bit more and maybe had the those separated, like in your simulation study.
Mhm.
And I know there's like papers as well, which kind of talk about having this like ICC for compliers and things like that. So there's a lot more like extension that could be done in that area. But yeah, I decided to kind of generalize it a bit more instead.
Okay, thank you.
Thanks.
Thank you very much, Lucy. And I think, so thanks to Lucy again, and move over to our next presenter. Okay, so our next presenter is presenting online.
Yes, I'm on the
So
Zoom,
our
but
next speaker is Dr. Ying Zhang from the University of North Carolina. And Ying will be talking about regression diagnostics for the identification of influential data in cluster randomized trials based on marginal models. So is Ying ready to share their screen?
yes.
Okay, great. Thank you. Nice to hear you. So welcome, Ying, and I'll hand over to you now. Thank you.
Hi, everyone. I'm Ying Zhang. I'm the PhD candidate in the University of North Carolina at Chapel Hill. Today, I will talk about identifying the inferential data points in the G analysis of CRTs based on regression diagnostics using paired estimating equations and MAEE. The marginal mean model for CRTs are commonly used because of it provides several advantages. First, the most important is that it provides populational average interpretation for intervention effects. Moreover, with sandwich errors estimators, it's very robust to the misspecification of the working correlation. Because of G is very flexible, it could apply to different types of outcomes and link functions. Moreover, directly modeling the ICC on the scale of outcomes is according to the contour statement on CRTs. Furthermore, Prentice in 1988 proposed the paired estimate equations, which could further estimate ICCs and their standard errors. Here I listed marginal mean model and marginal correlation models for multi-period CRT. On the left-hand side, you can see it's a very general marginal mean model with average intervention effects and a categorical periodic effect, as you always do in the GLM-like. The marginal mean outcome MUIJK is linked to the periodic effect beta and the intervention effects delta through the link function G. On the right-hand side, you might not that familiar, but it's very useful in estimating the ICC parameters alpha using the mean correlation model. The row part is the marginal mean pairwise marginal mean correlations for the observation pair, and it links through the ICC parameters through the link function H. The Z part are the queries on the specific correlation structures. For example, if the researcher chooses to use a nested exchangeable correlation structure with identity link, the Z will be indicators for the first column as the within period indicator, and the second column will be the across period indicators for the within period ICC alpha 1 and the across period ICC alpha 2. Then using the two marginal models, you could set up the estimating equations. The first row is the most general used estimating equations for the marginal mean, including the periodic effect and the intervention effects. And the second part is the paired estimate equations for the marginal correlations. So using this paired estimating equations, we could estimate all the parameters in the two models very efficiently. Worth of note that the RI part is the empirical pairwise correlation vectors for all the within cluster pairs proposed by Prentice 1988. But many researchers has been found that the Prentice unadjusted paired estimate equations will have some bias on the ICC estimations. So for the CRTs with a small number of clusters, such as the number of clusters less than 40, Praiser in 2018 proposed the matrix adjusted estimating equations, which modified RI part with the cluster average. So the MAEE has been shown that it could reduce the ICC parameter estimations and is applicable to CRT as few as 8 clusters. Then for the regression diagnostics for CRTs, it's very commonly used to identifying how deleting individual data elements will contribute to the parameter estimations. Here, I used the one-step deletion diagnostics proposed by Prison and Kakish in 1996. It's very computational efficiently, and it could approximate their exact deletion diagnosis very efficiently. We will denote the one-step deletion diagnosis as d beta, which is the change of the beta estimation after deleting one data unit n from the full data set. Moreover, the one-step quick distance is the multiplication of d beta with weighted by the variance matrix in the middle. Then I will use an example of the Connect Home study to illustrate how to use the MAEE method and how to conduct regression diagnostics for CRT with a small number of clusters. In this example, Connect Home study, it adapts a longitudinal and cross-sectional design with only 6 clusters, but with 22 periods. It wants to test one intervention to help those patients transitioning from skilled nursing facilities to home care. Here, the main outcome is a count outcome. It's the number of acute care use days with 6 days post-charge for the patient from the nursing home. Here, we use an average intervention effects model with linear periods because they are more vivid than the clusters. If we use categorical periods, the degree of freedom for t-test will be negative. So we want to use categorical periods effect here. The exponential of delta is explained as incidence ratio. Then under the nested extramural correlation structures, we could use the SAS macro MAEE to estimate the parameters and conduct regression diagnostics on cluster and cluster period level. Here, the table 1 listed marginal model results for acute care use. We found that the G with UE that firstly proposed by first proposed by Prentice will tend to underestimate the ICT parameters compared to the GMAEE for CRTs due to the small number of clusters in the Connect Home study. So here's the bias from the GUE. Then use GMAEE, the intervention is associated with around 25% of reduction in the number of acute care use days compared to the control group. Then here is the regression diagnosis results in the Connect Home study by the cluster level. Here on the left and the right side, you can see the 2 bubble plot. On the x-axis, they are the exact deletion diagnostics. On the y-axis, they are the one-step deletion diagnosis proposed by Praiser and Kakish in 1996. We could see that those one-step deletion diagnostics approximate their 4 iterative counterpart quite well in the cluster level. Moreover, the cluster with the first ID is the most influential clusters. That is the first transitioning steps with the most intervention periods. It's identified because of the greatest quick distance and absolute change in the intervention effect estimation. Moreover, it also has the greatest cluster size. Then after deleting the first clusters, we found that the intervention effects completely change from reduce the number of clusters, change to increase the number of clusters. So this cluster is really important, and it's very important to avoid missing this complete cluster. Then we have the regression diagnostics by the cluster period level in the Connect Home trial. On the left part, we also show that the one-step quick distance highly similar and almost agree with their fully iterative counterparts. And on the right side is the absolute value of d beta, indicating by the red color. If it's darker and redder, it means more changes of the intervention estimation after deleting this cluster period. We found out that those cluster periods closer to the transition steps influence the intervention effects more than those in the beginning or the end of the trial. And here's all the conclusions. First, using the marginal mean models actually support the consort statement on step wedge CRTs and including reporting ICCs. Moreover, for the analysis of CRTs with a small number of clusters, we recommend to use bias corrected sandwich variance estimators and bias ICC estimations with MAEE. For the regression diagnostics, it's very useful in identifying the most influential data units in CRTs, and it's very important to avoid those missing data in the transitioning steps in the step wedge design. And thank you all. Do you have any questions?
Ying, please. So thank you very much, Ying, for a very nice presentation. I think, first of all, we'll see if there are any online questions. So I think not. So any questions from the room, please? Jess, thank you. Oh, yes, sorry.
Thank you, Ying. This is Jessica Kaiser from Monash University. Really interesting work there. It seems to really iterate what we found in information content work, where those cluster periods near the time of the transition are the most influential. It's really nice to see that reiterated and emphasized here in this example of an actual trial. So that is more of a comment than a question. But have you thought about, I do have a question. Have you thought about the links with the information content paradigm, how that relates to your work?
Oh, yeah, thanks, Kelly. That's very interesting, because when I found this result that more impact on the beta estimations are very closer to the transition steps, I found it's very similar to your work. And your work is more about the variance changes after deleting this cluster period, but our work is mainly focused on how the beta estimation changes after deleting this cluster period. And your side is more on the design and the power of the analysis. Our work are more on the diagnostics after we get the full data. So I think it's actually a full pipeline if we could combine the two methods together.
Yeah, no. Yeah, I agree. It's really nice to see. I guess it's also related to the Matthews and Forbes work as well, which perhaps that's more directly applicable here. Andrew, any comments? No. No, you don't.
Yeah, no, we have expressions for the actual coefficients, and I'm sure that deletion diagnostics will show up the same cells that have got the highest coefficients in the linear combination. But look, that's for linear mixed models. This is much more general for binary data. So this is really nice work.
Thanks.
Thank you, Andrew, and thank you, Ying. And I think we'll move over now to our next series of talks, which are not rapid fire talks, but full talks. So our first speaker this afternoon is Kevin. Kevin would like to come up. Thank you. So Kevin is from the University of Newcastle, and Kevin is going to continue the Bayesian theme. Seems like lots of Bayesian work is happening in Newcastle. So Kevin is going to talk about, I think, Bayesian analysis this time. So thank you very much.
Well, that's not me. Point out when you see the time. Yeah, that's there you go. Oh, lost my timer now. Give me 2 seconds. I know, but I need to know whether I need to hurry up or not. Yeah. So this morning, Faye talked about Bayesian design of cluster randomized trials, and now I'll combine that with a Bayesian analysis as well. So first of all, let's set the scene. So we're going to be thinking about a 2-arm parallel group cluster RCT with a continuous outcome. And there's my version of the picture that everyone has about how cluster RCTs work. So the standard way to do this, the standard design of an analysis. So first of all, for the design, we would typically choose a sample size via a power calculation. So we choose the smallest sample size that gives a certain level of power, 80 or 90%. In order to do that, we need to know what analysis we're going to do following the trial. And so the typical thing to do is to look at a Wald test on the treatment effect as part of a mixed effects model. And we'll see the mixed effects model on the next slide. And therefore, success of the trial would be a significant treatment effect via this Wald test. So in order to conduct the power calculation to begin with, as Faye talked about this morning, we'd need a few things. So first of all, we typically use an MCID, a minimal clinically important difference on the treatment effect. we could alternatively use an estimate of the treatment effect. And then also we need some estimates of some nuisance parameters. And the nuisance parameters will become clear in a second, but actually Faye already spoiled it by talking about them this morning. The concern that we might have around whether or not we've got an appropriate sample size would be that both the power and therefore the sample size can be sensitive sometimes to these estimates of the nuisance parameters. And Faye talked particularly about the ICC this morning, and also sometimes the MCID on the treatment effect. And so if we're not confident in those estimates, if we have some uncertainty in those estimates, then we may end up with over or underpowered trials. So an alternative that certainly gets around that concern would be to do a Bayesian design of the trial. But if we're going to do a Bayesian design of the trial, maybe to be more consistent, we might also want to consider doing a Bayesian analysis as well. So let's talk about that. So how would we do a Bayesian analysis? Well, we'd start off from the same linear mixed effects model that Faye talked about this morning, where we ended up with the Wald test. So we have response Y for patient I and cluster J. We assume it's normally distributed. Maybe we've had to take a transformation with some mean for that individual and some within cluster variability sigma squared W. And then we have a linear predictor in which lambda is the overall mean response. Delta is the treatment effect, so xj there is an indicator variable, which is equal to 1 if cluster j is in the treatment arm and 0 otherwise. And then we have some random effects, these CJs, which are random cluster effects. And like most random effects, what we do is we set them, can we see that on the screen? Yes, we can. We give them a normal distribution with 0 mean and some variance sigma squared, and this is the between cluster variance now. And then the total variance from this model is then just the sum of these two sources of variability. So we could then construct a Wald test for the treatment effect delta, but instead let's think about doing Bayesian inference. So to do that, I need some prior distributions. So marginal prior distributions for the different parameters. So for the two fixed effects, the mean response and the treatment effect, suitable forms might be normal prior distributions, and then we need to choose values for M and V in each of those. And then if we want to exploit a little bit of conjugacy here, then we could give the variances inverse gamma prior distributions, which I've written out as gamma prior distributions on 1 over the variances, the precisions here. And again, we then need to choose R and S in each of these prior distributions. And perhaps in the analysis, a sensible thing to do is to say we don't want to influence the results of the trial using prior information. So we might want to pick fairly flat prior distributions on these parameters in order to avoid any undue, unseemly influence on the trial results. But how might we perform inference? Well, the standard way would be to do Markov chain Monte Carlo methods. And of course, we don't really have to program these up ourselves anymore. There's lots of handy software to do this. So I did everything in RJAGs here. So just another Gibbs sampler within R. And then we need some definition of or alternative to the hypothesis test. So perhaps we consider the trial to be a success if the posterior probability of a positive treatment effect is large. So if I set that equal to 95%, then that's sort of equivalent to significance testing at the 5% level. So we just look at the posterior distribution of the treatment effect and one of the quantiles of that essentially. And so that's all we need to do for the analysis. What about the design of the trial? So that's then influenced by the analysis. So I can't just do what Faye did this morning. I need to think about how this works in this case. Well, what are we actually choosing when we're choosing the sample size? Well, maybe what we're choosing is the total sample size. So if the cluster sample sizes are going to be unequal, so I'm not going to try and recruit exactly the same number of individuals from each hospital or something like that, then what I might want to do is choose as total sample size. And I see my nice equations have been messed up by something here. And this, if the equation was correct, would just be the sum of the sample sizes in each cluster. But then when we do the design, the power or the assurance in this case is going to depend on how unequal those sample sizes are between clusters. So I need to take that into account. So I need a model for these different sample sizes in the different clusters. So if n is my vector of sample sizes in each of my clusters, I could assume that this follows a multinomial distribution from my total sample size. So each individual's got to be in some cluster with some vector probabilities p. So this is the probability that a randomly selected individual is placed into a particular cluster. For each of the P's, and that wasn't supposed to disappear. And perhaps if in advance we don't really know which clusters are likely to have more individuals and which are likely to have fewer, then a prior distribution on this vector of probabilities as to which cluster you're going to go into a Dirichlet distribution is sensible because that's conjugate to the multinomial distribution, but a symmetrical Dirichlet distribution where all the parameters in the Dirichlet distribution take the same value imposes a prior belief that beforehand I don't know which clusters are going to be larger, which are going to be smaller. If I did, then I could encode that into the Dirichlet distribution instead. So then I need to choose the sample size. So just as Faye did this morning, I'm going to use this idea of assurance, which is our Bayesian alternative to power. And remember that this gives us the unconditional probability of trial success. So I'm not conditioning on the values of these nuisance parameters. And in fact, I'm not going to be conditioning on the MCID because I'm going to put a prior on the treatment effect as we saw as well. So this is a completely unconditional probability now for a particular sample size. And there's supposed to be an integral at the start of that equation. I shouldn't have submitted a PDF. I should have written it in PowerPoint. And so to get the assurance for a particular sample size NT here, I take a prior distribution over my set of parameters, which I've collected together into the vector psi here. Now notice this has got a D next to it. So this prior distribution is for the design now. This is where I'm going to impose what I believe about each of these parameters now. I'm now going to think about what my uncertainty on the treatment effect is. I'm going to think about what my uncertainty on these variances are. I'm going to think about what my uncertainty on the overall mean effect are. And the reason that this is going to work is because these are now informative prior distributions for my parameters. And I integrate it out. So I average over my uncertainty on each of these parameters, exactly as Faye talked about this morning. But instead of the power function, as Faye had this morning when she was doing a frequentist analysis, I now have a general probability that my trial is successful given some parameter values coming from this prior distribution. So how might I evaluate this assurance? How might I get my hands on it so I can use it to choose my sample size? Well, Faye this morning could use a simple Monte Carlo estimate of that by essentially sampling from my prior distribution on my parameters and then running each of those through the power function, evaluating the power function, and then taking the average. In my case, I still need to do that. So I still need to take samples from this prior distribution. So this integral, which would be here, but doesn't exist, I can evaluate that integral as a summation using a simple Monte Carlo sample. So I take samples from my design prior distribution, evaluate this term here, and then average over it. But now this term here is difficult because it depends on the posterior distribution of a Bayesian analysis, which isn't conjugate. And so now, every time I get a sample from my prior distribution to evaluate this term here, I need to do a full MCMC run and get a posterior distribution for my treatment effect and look at the quantile of that posterior distribution. So this is now more computationally intensive than Phase. So I've got an inner loop, which is my MCMC run, and an outer loop, which is my Monte Carlo samples. So it's a little bit more computationally expensive. But if I'm running a clinical trial for three years, spending half an hour calculating the sample size doesn't seem like a ridiculous thing to do. So I illustrated some priors that we could use there, some different types of priors. And the ones that I chose are numbers 1 and 2 at the bottom of this table here. But they're not the only choices of sensible priors here. So does the choice of prior have an effect on the posterior inference? Do I need to be careful about choosing my prior families? So what I've done here is I've picked 6 different sensible choices of prior distributions. All of them are pretty flat. So all of them are imposing not much information into my analysis. And then for 4 different scenarios, 4 different underlying parameter values, I've simulated some trial results and looked at the posterior distributions. So this is the posterior distribution for the treatment effect, and there's 6 curves on each plot here. And then these are 95% symmetric posterior credible intervals based on each prior distribution. So does the prior have an effect on the posterior? Well, you probably can't see very well from the top plot. So let's look at these ones. So these 2 left ones, all the 6 priors give almost identical posterior distributions, so we wouldn't be worried here. In this right-hand one, there are some small differences between some of the posterior distributions based on the different priors. In particular, this blue one here is much wider than the rest of them. And perhaps the green one, if that is indeed green, I think it might be light blue, looks a little narrower than the rest of them. So what I did when I used this in practice is I chose prior number 2, which is the red one here, which essentially goes with the group consensus if there's any differences, but typically there aren't really big differences anyway. Choosing either prior 1 or prior 2 is a good idea because there is some conjugacy we exploit there, and that allows us to run this much quicker. Effective sampling, how many samples do I need in the inner and outer loops? So my MCMC samples on the left-hand side, I've got 1,000. On the right-hand side, I've got 10,000. And then these are my number of Monte Carlo samples for the outer loop along the y-axis based on 100 different simulated trials. We can see that by the time we get to 1,000 Monte Carlo samples, it looks like we're getting pretty much good convergence on the true assurance, which is about 0.4 here. If we want to be really sure, we might use 10,000 samples instead. And so in the application, I basically chose 1,000 of one and 10,000 of the other, so we get accurate answers. And we can show that essentially, if you choose, if I just go back a step, if you choose one to be 1,000, another to be 10,000, and then you repeat it 5 times, then more than 90% of the time you get the same, you get the correct sample size. So this sampling variability doesn't have a strong effect on the sample size. If you do a few repetitions of your sample size calculation, you'll get the right answer. So in my final minute, I'll just take you through the same application that Faye did, but this time using the Bayesian method. So we've got this ICONS cluster randomized trial, systematic voiding program against standard of care, against usual care. I centered all the prior distributions on the estimates from the feasibility trial that Faye talked about this morning. So we've got some information on these parameter values, but we have uncertainty because the feasibility trial wasn't as large as the trial is going to be. I'm going to compare the approach I've taken in the slide, this fully Bayesian approach, to the standard power calculation that Faye also compared to this morning. Faye's hybrid approach using the MCID for the treatment for the treatment effect delta. I'm also going to extend Faye's hybrid approach, so we're still thinking about a wall test for the analysis, but now I've got a prior in addition on the treatment effect. So this third approach that I'm comparing to here has identical prior distributions to the ones I used for the Bayesian analysis, but instead of doing the Bayesian analysis, I'm going to pretend I'm going to do a wall test. So let's see if the Bayesian analysis actually has an effect compared to this hybrid method. So here are the priors, and here are the resulting sample sizes. If you remember from this morning, they were considering between 40 and 50 clusters. So I've got the different numbers of clusters in the columns here, the 4 methods in the rows. In each case, the blue one is the lowest sample size for that method. The red one is the highest sample size. We see that the power gives us, mine's 1-tailed, Faye's was 2-tailed, so the sample size is slightly different. The power gives us a sample size somewhere between 329 and 378. The hybrid MCID that Faye talked about this morning gives slightly larger sample sizes between 400 and 480, as she found this morning, so that's consistent with her results. In my prior for the treatment effect, we actually had quite good evidence that the treatment effect would be larger than the MCID. So that prior gave quite a lot of probability to treatment effects larger than the MCID. And what that's enabled us to do is to reduce the sample size required, because we're confident that the treatment effect is going to be larger than the MCID. So for the full hybrid approach, the sample size reduces to something between 215 and 252. And for the Bayesian approach, it reduces again to between 192 and 240. So what's happened between those two? The only difference there is the analysis. And a Bayesian analysis is more efficient than the hypothesis test that we've chosen. So in other words, the Bayesian analysis has come to the conclusion that the treatment is better more efficiently and more quickly, given the same data than the hypothesis test would. So Bayes' theorem is working in a slightly more efficient manner to update what's going on. So to summarize in my last couple of seconds, we can incorporate parameter uncertainty using assurance, as Faye and I have both shown. We can also, if we do a Bayesian analysis, take advantage of the efficiency of Bayesian inference in the analysis. Hopefully what we end up with is sample sizes that are more robust because they incorporate our uncertainty in what's going on. But actually, we could reduce the sample size required for trials if we had good, reliable prior information that the treatment effect is likely to be larger than the MCID. So all that works in the top paper there, and that's also the paper that Faye was talking about this morning.
Thank you, Kevin. Thank you very much. We thank Kevin. Time for a couple of questions. Are there any questions online? So questions from the floor? Some.
Thanks for an interesting talk. I wanted to see if you'd agree with perhaps a critique, perhaps, of something you said at the end, which was that Bayesian methods were more efficient. I suppose, and this comes from I've been working with people designing trial, and they go, oh, let's use Bayesian methods because we need less of a sample. Mm-hmm. And I say, well, you don't need less of a sample. You're just kind of using another sample's information and then adding on the trial information through an more informative prior. But inherently, the Bayesian method is no more informative, has exactly the same information. Would you agree with that as a sort of critique?
Yes, so I think that's absolutely true. So in this case, of course, I was using flat priors as well. But it can be the case that Bayesian updating can with fewer data points So with more efficiency, sort of come to the correct conclusion a little quicker than some hypothesis tests, but just because of the way the hypothesis tests are constructed. Now, of course, you can construct other hypothesis tests, but there is evidence that is sometimes true. But yes, in general, I think your point stands. Yes.
Thanks.
Thank you, Sam. Any other questions? Andrew.
Hi, I just wanted thanks for the talk. I just wanted to sort of confirm my understanding that there was lower sample size with the sort of the Bayesian method than the full hybrid. And essentially that was driven by assuming a treatment effect bigger than the MCID. So is that right? And could you in a sense have used the traditional method, but just been more optimistic about the treatment effect?
So it was in the design prior. So when I was doing the design, it was assuming that prior distribution gave quite high probability. So more than a half. So if the probability is more than a half in that design prior, that the treatment effect is larger than the MCID, then you're likely to see a drop off in the sample size. Whereas if that probability is less than a half, you'll see an increase in the sample size. That seems to be what it is. So yeah, you could change the MCID, but I think then it wouldn't be the MCID. It would be a larger than MCID. It would be a treatment effect of interest or something. Yeah.
Okay, thank you very much, Kevin. So let's say thank you to Kevin again. And our next speaker is Rhys. While Rhys sets up his presentation, I'll just tell you what Rhys is going to talk about. So Rhys is going to tell us all about how to estimate ICCs for binary data and longitudinal cluster trials. So I'm sure we're all eager to hear this. I know I am. A very practical problem.
What are we talking about estimating ICCs for binary outcomes in longitudinal cluster randomized trials? All right, so this is going to be a simulation study style talk, and what I'll be dealing with is how best to estimate ICCs from cluster randomized trials with binary outcomes. So an approach that's really quite appealing is instead of caring about that they're binary outcomes, you just assume you treat them like they're continuous outcomes, and you fit a linear mixed model as per usual and just read off the correlations from that. Now, for cluster randomized trials with just simple non-longitudinal ones with one correlation parameter, this is investigated back in the 90s and found to work pretty well. However, nobody's really done a lot of work on it in longitudinal cluster randomized trials with two correlations and this more complicated correlation structure. So that's what this talk is mostly about. We're going to be comparing it to some other GE-based methods. And we're going to be looking at things on the natural scale, so the untransformed outcomes, so correlations on the natural scale. Okay. So here's the sort of data generating model. We'll just be looking at, we're just taking sort of, we only care about the prevalences and the correlations. So we'll model the prevalences as this quite simple model with time effects and treatment effects, where beta J are the time effects. And then the correlations will just have this block exchangeable or nested exchangeable model, where we just have one correlation for observations in the same time period in the same cluster, and a different smaller correlation for observations in different time periods. And that's just smaller by a factor of R, this cluster autocorrelation. All right, so the estimators we'll be looking at, the first three are linear mixed model based estimators, and the last two are GE ones. So we've got the, well, I'll get into them in detail in the next slides. We've got ANOVA, REML, and EML estimators for the linear mixed model based ones, and then we've just got an unadjusted GE and a more modern adjusted GE. Okay, so the linear mixed model based estimators, we're basing them on fitting this model. So it probably looks quite familiar to you. There's a time effect to the beta, there's the, oh, do I have a mouse? Yep. There's the treatment effect, there's a cluster random effect, a cluster period random effect, and the residual, of course. And this gives us that block exchangeable correlation structure that we wanted. And of course, you can work out the correlations from the variances of the random effects. All right, so the so-called analytical estimator is one where you just estimate the variance components using ANOVA, and then you just plug those variance components into that formula on the last slide, which I've given here again, but in terms of the estimates. And then that gives you the estimated correlations. So very simple. The REML estimator, again, we're fitting the same model, but we're doing it with restricted maximum likelihood estimation. We're doing that with LME4 in R. And this one turns out to be equivalent to the analytical estimator, except if a variance estimate is negative, in which case it truncates it up to 0. So you'd expect similar performance, but slightly more positively biased, perhaps. And then we have the ML estimator, which again is the same thing, but with maximum likelihood estimation. Okay, if we move on to the GE-based estimators, we'll just have a simple unadjusted one for covariance and mean parameters simultaneously, based on the Zhao and Prentice paper. And this is our unadjusted GE estimator. And then we have the much more recent one from the Lee et al. 2022 paper on the marginal modeling of cluster period means. And this one is our final estimator, the MAEE method, which we've already heard talked about today. All right, so our simulation setup. We've got a few different parameters. We've got some design parameters at the top. Oops. And some correlation parameters we have to look at various values of. And then we have a couple of different designs. We're only looking at cluster crossover and parallelism for this. All right, so now we have results. There's a lot on this slide, and I'll try and talk you through it. And hopefully it's at least a little bit visible. Lost a bit of resolution here, but I'll talk you through and it'll be all right. All right, so first what we have on the y-axis is the bias of the methods, and each method is a different, well, should be a different color line here, but I'll tell you which ones they are. It fits a pretty simple pattern, so you'll be able to work out what they are in general. The three, and then each vertical line through the plot is one configuration, one scenario. So the two left panels are estimating the cluster level correlation, and the two right panels are when we have estimates of the cluster period level correlation. And then the top panels are for the parallelism design, multiple period parallelism. And then these bottom panels are the cluster crossover design. Well, that's not very readable. Okay. All right. And then I'll talk you through what the loops are, what's happening with the loops. So the bottom axis is the number of clusters per sequence. So each of these little groups of 3 points is either 6, 10, or 30 clusters from left to right. And then this loop is the baseline prevalence. This loop is the number of periods. And this loop here is the number of observations per cluster period. So reading this off, this left data point is 0.2 baseline prevalence for periods, 100 observations per cluster period. So we have just same number of observations in each cluster period, which I didn't say earlier. Okay, I promised I'd explain the methods. These ones, there's two methods down here in the sort of the lower, more negatively biased ones. They're the GE method and the ML method, the unadjusted GE method. And then the three methods at the top that perform very similarly are the ANOVA, the REML, and the MAEE. And I'm not showing Monte Carlo confidence intervals on this because you really wouldn't be able to read the plot, but the ones at the top are generally covering 0 quite nicely, and the lower ones are not. Okay, so one thing we can look at in these plots is not just what's changing over the plot, but what's staying the same. So if we look at these two red boxes, these are basically identical scenarios, except that in the left red box, there are 4 periods, and in the right red box, there are 8 periods. And you can see that actually the results look very similar across both boxes. So, and that sort of holds true across most of the graph with like tiny changes, but it really seems to be the fact that the case that the number of periods doesn't affect the bias very much for any of the methods really. Now we can do the same thing, but with the baseline prevalence. And we see that again, that doesn't seem to affect the bias very much. There's a little bit of change, but generally those two parameters aren't very important. And that in itself is pretty interesting. All right, so since we know that those aren't very important, we can fix them at a couple of values, and then we can look at what happens when you change correlation values. So now x-axis is the within period correlation, and the 3 data points in each series from left to right are that within period correlation is 0.01, 0.05, and 0.1. And so you can see as that gets higher, the bias seems to get worse certainly for the negatively biased methods. There's also, if you kind of look up here, there's a little bit of differentiation now between the 3 other better performing methods in terms of bias. So with small correlation values, suddenly the REML is not doing so well, and with larger correlation values, the MAEE is not doing so well. All right. So we've been looking at bias up until now. We can have a quick look at the variance as well. And in this case, the scenario's turned around. Now the 2 methods that were doing poorly in terms of bias are doing better in terms of variance. And they're the lower ones on these plots. And apart from that, it's not too much more interesting happening. This is the MSE. I'm going to just skip over this because it's come back to it later. I did put the confidence intervals on that one, but now what this slide is about is that we've been having some very similar performance for the ANOVA, the REML, and the MAEE estimators. So the question is, how much of that is they work about as well on average as each other, or how much of that is they're actually just giving very similar estimates every time? And the answer is much closer to the latter. Oh, it's very hard to see on there. Okay, so this is sort of a scatter plot of joint distributions going on here. So this is ANOVA, this is the this is the REML, and this is the MAEE. And you can see that generally they're giving very similar estimates, and the main variation is coming from the stochastic variation, so the between replication variation. So really they're all quite similar, with a lot of variation between replication. Okay, so to summarize what's been going on, well, LMM estimators and GE estimators can both do pretty well in terms of estimating the ICC and in terms of bias. Perhaps this is surprising with that very simple, even the ANOVA-based estimator does all right. Despite the maximum likelihood and the GEE, the unadjusted GEE being consistently negatively biased, they do have slightly lower variance, which you might care about since the variance is quite high. ANOVA and REML, well, we know they're identical for non-negative variance components, and that REML only ever increases the variance components. So you sort of expect that would have an effect on the bias. But generally it's, I guess in the scenarios we showed, it's rare enough that it doesn't have a huge difference most of the time, except for when the correlation parameters are quite small and close to 0, and there are very few measurements. Not clear why MAEE is so similar to those two as well, but quite interesting. So in conclusion, we would recommend any of the ANOVA, REML, or the MAEE estimators. So they have similar performance, as you can see. So you might want to choose between them for other reasons, like the REML has positivity. You might like GEs. You might like the simplicity of form of the ANOVA for trying to derive theoretical results. So it's up to you. All right, so that's the talk. Thank you. And here's some references.
Are there any questions online?
From John Presser.
Oh,
He
excellent.
says, I enjoyed your talk. Did you consider unequal cluster sizes or rare outcomes? Were there convergence issues for any methods?
Oh, so we didn't consider unequal cluster sizes, and I think that is really something that we would like to consider and would use in the future. There's problems with the ANOVA with that, and that you don't then have the nice properties that you had with these equal cluster sizes, because it's no longer necessarily balanced designs, and that's also why you don't have step wedge in there. Yeah, as far as the convergence issues, we were steering clear of that a bit, but it's definitely something we should look at. Thank you.
Thank you. Any other questions? Okay, I think we'll move on. So let's say thank you again to Rhys. Thank you. And our next 2 speakers are going to be online, and they're 2 rapid fire talks. So our first talk is from Kylie Lange from the University of Adelaide. And Kylie is going to be talking about partially cluster randomized designs. So Kylie, if you can start speaking, we'll hand over to you if that's okay.
Sure, thanks. So hopefully you're seeing the title slide.
Yes, we can see your slide.
Excellent, cool. Yeah, this is a very non-technical talk, so thanks to Lucy for kicking us off in that genre. This is part of my my PhD work on partially clustered trials that I'm doing in Adelaide, Australia. It's often assumed when we're talking about clustered data that all individuals belong to a cluster. So this is the framework that we're usually assuming when we're talking about cluster randomized trials and step wedge trials, for example. However, many trials involve partially clustered data where only some individuals belong to a cluster. So clustering we can actually think of as a continuum from fully independent data at one extreme to fully clustered data at the other. And partially clustered data then falls in the middle and consists of both clustered observations and independent observations. So my group's interest in partial clustering was motivated by the challenges encountered when working on trials in neonatology. So here the participants are infants and can include singletons and infants from multiple births. The intervention may be administered during pregnancy, like a nutritional supplement, or to the individual babies after birth. So working on these trials raised the issue of how to deal with the clusters of size 2 or 3 that result from multiple births when calculating the required sample size and in the analysis of these trials. So partially clustered trials occur in many different applied areas. However, they've received limited attention in the literature. These trials are difficult to identify and there's been limited methodology developed to guide their design and analysis. We proposed that the lack of standardised terminology for describing these trials may be hampering the development and dissemination of methods for partially clustered trials. And so we aimed to develop a taxonomy of the types of different partially clustered trials and the terminology to describe them. I'll be presenting just an overview of the results of this work that we hope will raise awareness of these designs, improve the reporting of these trials, and encourage the development of more methods for their use. So the designs of partially clustered trials can vary on a number of characteristics. Clustering may be present in all treatment arms or only some. The intervention may be administered at the cluster or the individual level, and the method of randomization that's used for the clustered observations can vary. However, there's two kind of defining characteristics that really dictate the specific type of design. Firstly, the clusters may exist before randomization, such as infants from a pregnancy, or multiple body parts of an individual person, which I'll say more about on the next slide. Or the clusters may be induced only after participants have been randomized, for example, by assigning people in the same randomized arm to education classes. Secondly, trials can use different randomization methods for the clustered observations. So the randomization may occur at the cluster level, at the individual level, or balanced randomization can be used to assign, for example, one member of each cluster of size 2 to the 2 alternate treatments. So these two design factors lead to 4 types of partially clustered designs. One where the clusters do not exist before randomization, and so randomization is performed at the individual level first. And then there's 3 designs for clusters that exist before randomization and differ based on the randomization method that is used. So I'll illustrate each of these 4 types of partially clustered designs for the case of 2 treatment arms indicated by the 2 sides of the panel, and with the observational units shown as filled circles. So individual randomization with post-randomization clustering refers to the case of individual randomization to treatment arms first, followed by forming clusters within some but not all treatment arms. So examples of this include individually randomized group treatment designs and facilitator effect designs. So this design's been relatively well studied to date, and it's referred to as partially nested designs in some fields. And our interest is more in the other cases where there are pre-existing clusters. So when clusters exist before randomization and each individual observational unit is randomized independently, we've termed this individual randomization within pre-existing clusters. So since units from the same cluster may be allocated to different treatment groups, the intervention must be administered at the observational unit level. And trials of this design have been used in fields including neonatal health, where infants are randomised individually and may include multiple births. In ophthalmology, patients may have 1 or 2 eyes affected with disease and eligible for a trial. So with an eye level intervention like surgery or eye drops, then individual randomisation may be used, leading to this design. With existing clusters and randomisation at the cluster level, we get this situation where the members of each cluster are all allocated to the same treatment, which is analogous to our standard cluster randomised trial setting. So this design can be used for trials of cluster level interventions like systemic medications in ophthalmology or interventions administered during pregnancy. Cluster randomisation may also be used in studies of interventions that are administered at the observational unit level, but for logistical reasons or participant preferences, which we know is a common issue when clusters are twins, then cluster randomisation may still be preferred. A trial can also be designed to balance the treatment allocations within existing clusters. So in this case, each cluster contains members assigned to both treatment groups, as in a crossover design. And this is commonly seen in settings of paired body parts, such as eyes or joints like hips or knees, where the clusters are naturally of size 2. So to learn how partially clustered trials are described in practice, we conducted a review of a convenient sample of partially clustered trials and discovered that the current practices for describing these designs are inadequate. There was no consistency of terminology or in how and where the clustering was described. So motivated by that, we reviewed the relevant consort guidelines to identify items on trial design that could be modified for partially clustered trials. And so from that, we've made 3 recommendations. Firstly, the title should just include randomised trial as in the standard consort statement. So while partial clustering is important, it's not necessarily always a major design feature if there's only a small number of clusters. So specifying this in the title isn't always going to be necessary. Secondly, trials should be described as partially clustered or involving partial clustering in both the abstract and the methods. This would facilitate better keyword searching for these kinds of trials and the related methodological work that might exist for them. And thirdly, the specific type of partially clustered design should be clearly described in the methods, such that the method of randomisation and what constitutes the cluster level and individual level units in the trial are clear. This could use the specific phrases for the trial designs that we have outlined, establish terms like individually randomised group treatment design, or be described in language appropriate for the context of the particular trial. So, for example, an ophthalmology trial using cluster randomisation of pre-existing clusters could be described in a methods section as shown here, specifying the partial clustering of eyes within participants and that eyes were cluster randomised. So my key message is that by increasing the awareness of partially clustered trials and adopting these definitions and terminology, we can improve the reporting of these trials and encourage more methodological research in this setting. A paper on this work is currently under review, and please get in touch if you're interested in details when that's published. My future work will be looking at sample size methods for the different types of partially clustered designs, which will be extending on work by my supervisor, Lisa Yelland, who has published design effects and online sample size calculators for the case of independent and paired data. So thank you, and I'll open for questions.
Thank you very much, Kylie. Any questions online? Any questions from the floor? Question from me, Kylie. So you talk about cluster designs within specific medical fields, or perhaps more of a comment. And I wonder whether you had thought about split mouth types of designs in dentistry. And I think they have a sort of established terminology there.
Yeah, that is something we did start to look into. I found that in a lot of the dentistry examples, we didn't see any examples where there were any singleton observations. They were kind of tended to be more complete, more balanced type designs. But I wouldn't be surprised if there are examples there or in other fields that we haven't turned up. They've been quite difficult to identify. So yeah, any particular examples I'd really appreciate.
Okay, thank you. So unless there are any more questions, I'll say thank you again to Kylie. Thank you, Kylie.
Who is Peter Smith, who's a professor of tropical epidemiology from the London School of Hygiene and Tropical Medicine. Peter's had a long and distinguished career. He's worn a number of hats in that time. For example, he's worked with the International Agency for Research on Cancer as well. As part of some of these roles, and of particular interest to a room full of cluster and stepped wedge experts, Peter had a key role in designing the first ever stepped wedge trial. So he is, if you like, the godfather of stepped wedge. And I'm delighted that he agreed to come and talk to us and share his experiences from the birth of stepped wedge and beyond. So Peter, over to you.
Thanks very much. Okay, well, it's very, very nice to be here and talk to all you stepped wedge trial experts. I don't know if the trial I'm going to talk about was really the first ever use of the stepped wedge design, but what I can say with some more assurance, it was the first trial of this design that was called a stepped wedge trial, because I think we invented the name. So if we did nothing else, we actually christened it. So what I'm going to talk about is this trial that was done in, thinking about it started in the early 1980s. The trial is still ongoing 40 years later, with some issues, which I'll touch on briefly at the end. So it didn't quite work out as we had hoped originally, but I'll just give you a little bit of the background as what led to the setting up of the trial and what's transpired. It was an intervention against hepatitis B. Hepatitis B is a big global problem, and it's thought to be the major cause of liver cancer globally. There were about, or at this time, I'm talking about the early 1980s, there were about 250,000 cases of liver cancer globally, very fatal condition, survival very poor. Common is male cancer in the Gambia. I'm going to talk a lot about the Gambia, which is where the trial was conducted. And it's thought probably 80% plus of liver cancer cases are attributable to the association with HBV. That wasn't hepatitis B virus. That wasn't known at the time, but it was strongly suspected that this virus was actually the cause of a substantial proportion of this cancer. So it's a very common cancer. There was this strong evidence that when you get infected with hepatitis B, sometimes you get infected and you sort of throw off the infection. Other people, about 20% of people who get infected, actually become chronic carriers of the virus. And they become chronic carriers for life. And it's that association with the carrier state and the risk of liver cancer that was thought to be the strong association. So if you could prevent the carrier state, then you potentially prevent liver cancer. There's quite strong evidence, both from animal studies with sort of animal models of hepatitis-like viruses, that you could induce liver cancer. You could show that the virus, hepatitis B virus, was actually integrated into the tumor of human tumors. So although there was direct causal evidence was not there, it was strongly suspected that this was actually going to be a vaccine against this virus would be a major intervention against this cancer. Now, at that time, there were hepatitis B vaccines available. They were derived essentially by harvesting blood plasma from hepatitis B carriers, and then, as it were, inactivating the virus and using that inactivated virus as the vaccine. It sounds a little bit risky these days to take, to my knowledge, there weren't any knowledge where the virus wasn't inactivated, and it was a very effective vaccine. At least the evidence at the time we were doing it with these plasma-derived vaccines was that they were shown to give quite good protection against the carrier state for up to about 5 years. And beyond that, there really weren't any data at this time in the 1980s. It was a very expensive vaccine, and consequently, it wasn't really used in other than high-income countries. At that time, it was about $100 a course. I don't know what that translates into now, but quite a lot more than $100. But the price was falling. And importantly, there were new recombinant vaccines were being developed that would replace these plasma-derived vaccines. And they have become very cheap. So they're just a dollar or two now. In West Africa, where this trial was conducted, the first infections with hepatitis B virus occur in infancy. And by the age of 10, about 90% of children are infected. And the carrier state is strongly related to the age at which you're infected. So if you're infected in the first year of life, you've got something like a 60% chance of becoming a long-term carrier. And as you get older, the association between becoming a carrier, a long-term carrier, and infection is much weaker. So it's really if you want to have a serious impact on the disease, you have to get a vaccine in early. And basically at the time the trial was done, for obvious reasons in terms of the cost of the vaccine hadn't been introduced into any countries in sub-Saharan Africa. Just to orientate you that are not familiar with where the Gambia is, there's a map of the Africa on the left and shows the Gambia on the sort of extreme west coast. And this is just on the right-hand side is a blown up map of it. It's, if you like, a colonial artifact. Senegal was essentially a French territory, and Gambia is essentially a British colony for some of its time. And to some extent, whether it's apocryphal or not, I'm not sure, but the boundaries were defined by how far a British warship could fire a cannon in any direction. It doesn't fit totally well, but it's of that nature. So it's a very odd country. It's English speaking. Senegal is well, the main language is English, and Senegal, obviously, local languages predominate. It's a small country, and that has a lot of advantages for the sort of study I'm going to talk about. It's only about sort of 300 kilometers long, even less wide. It's got roads which vary in quality, but more or less run to the end of it. And has a very good vaccination program. Even then, it has a very good vaccination program with very high coverage compared to the much more difficult to reach areas in other parts of Africa. There'd also been a Medical Research Council unit, British Medical Research Council unit, that was set up there. In fact, they just had this last week. They've had their 75th anniversary. So that was set up before independence. Gambia had independence in 1965. So there's been a long-term Gambia MRC research unit there, and that's had quite a big influence on the medical research that's been conducted in the country. It's a small population. In the 1990s, it was less than 1 million, so it's really quite a small place. That just shows some data. It's not very much data, but it's some data from next door in Senegal, showing this association between the age at which you're infected with hepatitis B and your risk of becoming a carrier. And the numbers are small, but these have been sort of substantiated in larger numbers. It goes down quite rapidly with age. So if you're infected in the first year of life, there's a high chance that it goes down progressively. The actual hepatitis intervention study was the idea for a study was attributable to someone called Robin Ryder, an American epidemiologist who studied at the London School, did an MSc there, and then after leaving the school, he went to the Gambia to work under someone called Hilton Whittle, who worked in the Gambia for very many years as a virologist, particularly interested in hepatitis. And he went there to conduct a case control study on risk factors for liver cancer, including hepatitis B infection. But while he was there, he conceived this idea that why don't we introduce hepatitis B vaccine in the Gambia and then follow them to see if they were protected against liver cancer in adult life. So quite a bold thought, and actually translating that into a study proved to be quite a long process for a year or two. He took this idea to the then director of the International Agency for Research on Cancer, someone called, an Italian called Lorenzo Tomatis. IRC is, as some of you will know, is based in Lyon. It's essentially the cancer research arm of World Health Organization, of WHO. It's separated by from Geneva. They have their sort of independent funding through member states. They function fairly independently from the rest of WHO, but they are part of WHO, and their brief is to do research on cancer and cancer etiology. So Tomatis did two things. Basically, he talked to Merck. Merck Sharp and Dohn had large supplies of this plasma-derived vaccine, but this was rapidly being replaced by this genetically engineered vaccine, and so sort of less beneficial interpretation is they had a lot of vaccine they didn't know what to do with. A more positive response was that they donated this vaccine, a large number of doses, to do a study of this kind, although the actual definition of what the study was going to be was a little bit unclear at that stage. And then Tomatis, using the sort of his links to the Italian government, managed to persuade the Italian government to actually contribute something like $6 million to actually setting up a study. So Tomatis was unfortunately now died, but was very important in actually setting it up. And the sort of background to the study, this was a meeting that I went to at WHO in 1983 on prevention of liver cancer. And it was recognized that although it wasn't certain that hepatitis B virus actually caused liver cancer, it looked a pretty good bet. And if you actually could get high coverage with hepatitis B, you could potentially prevent liver cancer. And this would be the first cancer caused by a virus that could be prevented by vaccination. So that was really what Tomatis's excitement was about. There was a lot of suspicion at that time that viruses causes cancer. As we know now, a lot of cancers are caused by viruses, but at that time, the actual direct evidence of a virus causing cancer was less clear, and certainly that a vaccine might reduce that was even less clear. Of course, nowadays we've got HPV virus, papillomavirus, and others which are more established. But this was the situation at that time. And it was recognized that although it would be desirable to immunize on a wide scale with hepatitis B virus, it would be wise at the same time to organize studies to establish whether or not the vaccine was actually, one, reduced in the carrier state, and that could be done relatively quickly, although you'd have to see for how long it reduced the carrier state, and subsequently cancer. And that couldn't be done so quickly because we're talking about a disease which has onset in the sort of early onset in the people aged 30, 40, 50, and very little before that. So it would be very long studies. It was recognized that the best method of doing this would be some sort of randomized trial. Although this would present ethical difficulties if there was sufficient vaccine available to treat all newborn children, because the sort of circumstantial evidence of effect was really quite strong. And at present, and for the next several years, as proved to be the case, that was not the case. There was not enough vaccine available. The vaccine's expensive, supplies are very limited, so that some sort of trial could be considered. So a number of options were considered for using this donation from Merck Sharp and Dohn in the Gambia. First of all, the cleanest way would probably have been individual randomization, and where children would also get all of the vaccines that were in the extended program of immunization, but children would be randomized to either get those or they would get those and 4 doses of the HPV vaccine, which was first dose given with BCG shortly after birth, and then 2 more doses shortly after, then a booster dose at about 9 months. It was recognized this would be the most powerful design. It was also recognized that it would be logistically challenging, that this was being administered within the normal vaccination teams, which don't normally randomize. So actually organizing, not only that it was randomized, but randomized in such a way that when individuals came, they got 4 doses of the same vaccine or 4 doses of nothing, as it were, would be a challenge. And there were also ethics concerns about withholding a likely efficacious vaccine. But the fact was that without the donation of vaccine for this study, nobody would have been vaccinated. And the trial would have been conducted, and one can argue about the ethics of that. And we had some debates about, well, part of the problem is because Gambia is a small country and you could feasibly think about vaccinating everybody. If you're doing this in Nigeria, then you couldn't do that with this amount of vaccine. Suppose we expanded the trial population into Senegal next door. It's a very sort of artificial porous boundary between the 2 countries. We could just double the size of the trial population. Anyway, those were the sort of arguments that we used to justify potential use of a randomized allocation of the vaccine. The other option would be cluster randomization. That also would be a powerful design to show an effect. The logistic challenges would be less, because then you'd have sort of some clusters give the vaccine, other clusters wouldn't give the vaccine, clusters being in this case vaccination teams. And there would still be some ethics concerns about withholding a likely efficacious vaccine. But again, there was a limited donation of vaccine and nobody would vaccinate it if the trial wasn't done. And the cancer agency was interested in research, and it wasn't actually interested in just distributing vaccine without evaluation. So the other option, which is what we ended up with was the phased introduction of EPI vaccines versus EPI vaccines and hepatitis B vaccine. So the vaccine would be sequentially introduced into different vaccination teams in a random order over a 4-year period to include about 120,000 infants, which was the sort of 4-year birth cohort for the Gambia, during which time 60,000 would be going to teams which got the vaccine, and 60,000 teams would be going to teams where 60,000 would be going to vaccines without the vaccine. And we had a lot of discussion of this, and the actual design was conceived at a weekend meeting we had in Lyon with Robin Wright and Nick Day. Some of you may know Nick was the head of biostatistics at the International Agency for Research on Cancer at that time, and subsequently on to be the head of the MRC Biostatistics Unit in Cambridge. And it was that weekend meeting that we actually christened it the step wedge design, and showed it was really almost as powerful as a cluster randomized trial, about sort of 70% as powerful. There were ethics concerns, again, about withholding a likely efficacious vaccine, but full coverage would be achieved over 4 years, by which time the hope was that the vaccine price may have fallen to affordable levels, and then the program could continue. That was another hiccup that I'll mention a little bit later. So there were a lot of different ethics committees involved in this study. There's a well-established MRC Gambia Government Ethics Committee in the Gambia, which looked at all work that was being done under the auspices of the Medical Research Council and others in the Gambia. The MRC in London had an ethics committee. The International Agency in Lyon had an ethics committee, but they got a little bit cold feet about this, and they thought, well, we better pull in WHO Geneva as well. So basically, the various proposals for different designs went over a period of time to these different ethics committees. And you can see the result there, that basically the Gambia and the MRC were happy with any of the designs. WHO, either in Lyon or Geneva, were unhappy with the first 2 designs, and I put them not with a smiley face, but with a sort of, not quite smiley face. They, in the end, they said, well, okay. I don't think they quite had the smiley face, but anyway, that, and whether this would go through now, if we did, I wonder. And this then is the design of the study. Basically, it was, at that time, there were about 17 different vaccination teams which covered the whole country in the Gambia. And the proposal was that it would be introduced, new introduction every 3 months. And so in the first month, you have, we only thought about the sort of crosswise comparison. We didn't really think about the longitudinal comparison. We had to compare the incidence of liver cancer in this group compared to this group. And then in this, it would continue in that group. And then we compare that group to that group, and so on and so on, the normal step-by-step sort of design. And that would be over 4 years. You could argue whether, what does it really take 4 years to actually introduce a vaccine like this? Well, probably not. But anyway, this was accepted. And then by the time 4 years had passed, there would be national coverage. And that sort of designing this was one thing, actually doing it was another. Andy Hall, who used to be at the school, some of you may know, went out to the Gambia, and he was charged with actually implementing the study. So he, with Hazel Inskip, who looked after a lot of the data, now at Southampton, they joined. I've run out of time.
Your share. Just click that onto your share. Yeah, that's perfect.
Sorry about that.
Right, you have that in your pocket as well.
Okay. Do you want me to start again? Okay, I hope the sides are sort of self-explanatory regardless of what I might have said. So Andy was charged with doing it, no small feat. You can imagine he and a large team of people, but it was done. When we got to this stage, that was the sort of, if you like, the end of the interest of IRC. IRC sort of said, we've got these data, we'll now pack these away, we'll wait for 40 years and see what happens with respect to liver cancer. But the Gambia government quite reasonably said, well, yeah, you've got national coverage, but what's going to happen now? And the vaccine price hadn't fallen quite the extent it had been expected by that time. And it looked as though there might be a hiatus in there being no vaccine at that time. And that would have been ethically pretty difficult to justify. And the Cancer Agency accepted that. So they did a lot of scouting around to try and find resource. And they did manage to find somebody, I think a Swedish government, would actually pay for continuing supply of hepatitis B vaccine until it became much more widely available at a cheaper cost. So that program was continued, but it was a hiccup, and it's obviously an issue in all cluster randomized trials as to what you do once you get to the end of the clustering. The things that were done in the meantime were there were various studies done to look at what the effect on infant vaccination would be on carriage of the hepatitis B carrier state. I'd said when the trial started, it was known that it was protection for 5 years. But now subsequent studies were done in subsets of the population in the Gambia, showing that infant vaccination actually gave protection, very high protection against the carrier state for at least 20 years when Compito and colleagues did that study again in the Gambia. So that was the basic design of the study. What's happened since then, and this is what's happened since then is this shows just the proportion of the population in Africa and globally of children who are getting hepatitis B vaccine. And you can see that for the period when the trial was starting, it was very low, but subsequently hepatitis B has become one of the standard vaccines in all immunization programs, and is high coverage, 76% coverage in Africa, in sub-Saharan Africa as a whole. The original aim had been to link the vaccination records of infants included in the study to cases of liver cancer
as they arose 30 or 40 years later. So for that purpose, a cancer registry was set up, which was hoped to maintain for 30 or 40 years, picking up cases of liver cancer that could be eventually linked when this cohort came through to whether they were in the vaccinated group or the not vaccinated group with hepatitis B. That was recognized was going to be challenging because you had to be able to link an infant to a 30 or 40-year-old. And identification information was collected, name, date of birth, mother's name, father's name, village of residence. But it's known that those were not very hard measures. People changed their names, they changed where they live. Some names are very common. So it was thought, and although they might be useful in trying to tie things down, it would be also useful to have a hand print and a footprint. So handprint and footprint were collected on all these 120,000 kids. There wasn't much experience at that time of actually linking, and probably still isn't, of linking a newborn handprint or footprint to an adult handprint or footprint. We talked a lot to Scotland Yard, who used sort of fingerprints at least for a lot of this purpose, but all of their, at that time, all of their linkage records were based on measuring the distance between whorls and lines on the fingerprints for the identification. And because these things expand with age, nobody's really, they said, well, we could write you some software to try and do that, but it will cost you a large amount of money. So nobody could actually, nobody had experience of actually linking infants to adults. The only hope would be that if you could actually link what you thought was the infant to what you thought was the adults and look to see if they matched. And that was the plan. Unfortunately, despite great efforts, attempts to link the liver cancer cases to the study cohort have been largely unsuccessful, due to a whole variety of reasons, some of which are just logistics and the problems of conducting a 30 or 40-year study with changing investigators and so on and so forth. So that the bottom line is that that's been largely unsuccessful. So what we're discussing now is what we can actually salvage from the original study in terms of actually looking at the impact on liver cancer. And what we're hoping will be possible, though this is still under discussion, is not so much using the step wedge design, but the step wedge design actually introduced hepatitis B into the Gambia, and then there was high coverage with the vaccine thereafter. And so it should be possible to actually see quite a strong, because it's probably quite strongly protective, we should be able to see quite a strong cohort effect between people who, as it were, born before the vaccine was introduced and those born after the vaccine was introduced. But that's still a discussion which is ongoing, including with funders. So that, I think I can stop there. I think that's my sort of summary of where we got to.
Thank you, Peter. That was absolutely wonderful. I know there will be lots of questions. I'm going to use the chair's prerogative to ask a question or two, if I can fit them in. In relation to following people up and linking them, am I right in thinking that there was a plan to use the position of the BCG scar to code which trial arm individuals were in?
Yes, you are. That I didn't mention that because it didn't work very well. The plan was to actually, so because BCG, as you know, leaves a distinctive scar, not on everybody, on most people. The idea was that those who got the hepatitis vaccine would get the BCG on one arm, and those who didn't would get it on the other arm. We don't think that worked very well because maybe we've got 60,000, 120,000 children going through. We've got busy EPI teams, whether they always got it on the right arm or the left arm. It seems that didn't work very well. So it was a sort of check, but it turned out not to be all that worthwhile.
I mean, it was a brilliant plan. All you needed was for people to remember their birth date and to look and see which side of their arm, which arm they'd been vaccinated.
Yeah, and remembering their birthday is another issue. That people probably better now, but at that time, people had no particular reason to remember when they were born, and many didn't know when they were born. And that is an obvious issue in terms of long-term follow-up, that actually working out exactly how old someone is, which would be critical to a cohort study, has also got uncertainties associated with it.
Thank you. Are there any questions so far online? Not yet. And in the room, Liz.
Thank you so much for that wonderful talk. My name's Liz Turner. I was formerly at the London School of Hygiene, and it's wonderful to hear more about this study that we've all taken a close look at. I'm really interested to hear a little more about your weekend in Lyon when you came up with the terminology. I was very curious to know what other terms you might have considered and how, if there was agreement, consensus on the term stepped wedge design, or any thoughts and reflections on that process.
I don't think it's very profound. I mean, if you look at the picture,
yeah, exactly,
sort of wedge, but it's got steps in it, and I don't think it was any more than that.
And was it the very first one you settled on, or had there been a series? Do you recall if there were a series of other terms you considered?
To be honest, I don't remember. We might have called it a wedge design, but then stepped wedge sounded better. But
thank you. Thanks.
So Peter, were you aware, have you been aware of how popular the stepped wedge design became and other people?
Well, it's interesting. I mean, for many years, I think it sort of rested in the doldrums, mainly perhaps because, well, I don't know, because may have been other reasons, but we published the design. It was the only paper we actually wrote on the design, and it was several years after the study started, in cancer research, which is probably not the first place you go to sort of for methodology. And I don't think there were really many step wedge designs done for somebody may have done research on this, but for some years after this. But obviously now I'm aware that you can have a meeting with 40 people in the room. And it has, and you know, there are still a lot of the issues in terms of ethics and so on and so forth haven't gone away. I mean, I think they're the same. They were a bit more perhaps acute with this, with respect to, you know, the issues. This is sort of life or death vaccination. But I think, you know, many of the issues that we encountered, I'm sure people designing a step wedge design. I mean, I think I was on the sort of global health trials group that Wellcome MRC had for a while. And I know we saw a lot of step wedge designs coming through. And the question, and a frequent question is, why are you doing this as a step wedge? Do you really need to do it as a step wedge? I'm not saying it's overused, and it's obviously, but unless you can be sure what's going to happen after here, which is often a challenge, particularly if you're a researcher, but you don't have much control that goes up after here, then I think there are real issues in, you know, you've got to ensure, you know, the justification for the design is you're getting complete coverage. And if you can't ensure what's happening after that, then I mean, that's true in all trials, but it's particularly true when you use this design.
I agree. And we talk a lot about what the real reasons or justifications for a step wedge design are. People often say that the reason is that you give the intervention to everybody, but as you've said, only half of the infants in your study were vaccinated during the course of the trial. So it's not the case that everyone was getting the intervention. What was it about the design that you think swung those last two ethics committees that were holding out? What was the feature that they liked?
Well, liked. I think there was acceptance this was a potentially important study. And whatever you did was going to be ethically difficult. But if they didn't, well, I'm supposing here, I don't really know what happened. But if you didn't do this, you'd say we'd do nothing. And so nobody in the Gambia would get a hepatitis B vaccine, I think would have been the answer, because I'm not sure that Merck would have donated it just to the Gambia to use, as it were, in their program as part of the deal with the cancer agency as part of their research program. So I think it was probably sort of the end of the road, actually. But I'm speculating. I really don't know what went on inside those ethics committees.
It's fascinating. So was there enough vaccine at the start of the trial to potentially have given half of the clusters the vaccine right from the start?
Probably, yes. Yes.
So yeah, well, it was good for us who now study STEP Wedge that you that you alighted on that, but it seems like a slightly random happenstance.
Yeah, I mean, there would be enough to give everybody in the Gambia the vaccine for 2 years. But then after that, it would have been unclear.
Other questions in the room?
I mean, I don't know whether, you know, we're talking about 40 years ago now. I don't know whether this would actually get through an ethics committee now. We struggled then, and if anything, ethics committees have got much more difficult now than they were then. So
I think they love STEP Wedge trials, actually. Andrew.
Thanks very much. Brilliant talk, Andrew Kopas from UCL. I just wondered whether, how did it work with then withholding the vaccine for those children that were sort of born sort of too early? Because I mean, presumably parents or villages or teams might have been asked, you know, well, what about this child? They're born too early, but they're still quite young. Can't we have the vaccine too, please? Was there a problem?
I don't think there was a problem, but that's a problem with the introduction of all new vaccines. Whenever a new vaccine is introduced into the extended program immunization, otherwise, what generally happens is it starts being given at the age at which it's designed to be given. And if you've missed the boat, you've missed the boat. Sometimes there's a sort of catch-up campaign where you actually vaccinate widely. But I think it's generally the case with most vaccination programs that, you know, if the vaccine's not introduced and you've missed the age group, you don't get it. I mean, that did become an issue with this group because although by the age of sort of 10, most of these would have been infected with hepatitis B anyway, after which time the vaccine would be no good. When the study that Tom Pito and some earlier people did, when they were looking at people sort of 20 years later, they did actually test some of these people. And if they were still uninfected, then they did give them the vaccine. That was thought to be ethically necessary, but that was only a very small proportion of the total population.
Thank you.
I'm Andrew Phillips from Monash University in Melbourne, Australia. Thanks for a wonderful talk. I was interested when you said when you are looking at the sample size and power, you looked at the vertical comparisons between sort of treated and untreated. Because it's funny, in the intervening many years, it's gone from just the vertical comparisons to then realizing that there are horizontal comparisons and you can use both elements, but then horizontal comparisons are confounded by time trends, and then there have been some proposals for more robust methods that go back to vertical comparisons, which was where you started with then. So just wondering, do you have any recollection of the discussions about the problems with the horizontal comparisons at that weekend meeting, and if there were problems about time trends, and that was the reason why you chose very wisely, to use vertical comparisons in such a big and novel study?
Now, I think at that time, we were all purists, and we wanted to actually do the design with the least possibility for bias, recognizing that there will be temporal trends, and you can overcome those by sort of doing it within the time interval. And we really, I think it's all you guys have sort of developed the method to look at it both ways. But the sort of pure randomization is that one. After that, you're sort of getting a little bit beyond the pure randomization. You have to make assumptions about trends and allow for them and so on and so forth. So I don't think, perhaps naively at that time, we really gave much consideration. Of course, now, that's what we're thinking about. We're thinking about actually comparing what happened to these guys compared to what happened to these guys. And that is purely going to be a longitudinal comparison. But that's only because it's not been possible to actually do that individual linkage that we'd originally hoped would be possible. And that sort of study, I mean, that if we do manage to do that, I think it will be unique in Africa, but I don't think it will be unique, period, because the Taiwanese have done similar studies with respect to the introduction of hepatitis B vaccine and subsequent followed liver cancer, and shown it did have a profound effect on, the program has had a profound effect on liver cancer. But then the epidemiology of hepatitis B, for reasons which I think are not still fully understood, is different in the Far East than it is in Africa. There's much more perinatal transmission in the Far East than in Africa, so that you really have to get in a birth dose in the Far East, whereas in Africa that was less critical because there's much less perinatal transmission, although birth doses are being introduced in some programs. And also for other, the incidence of liver cancer is much higher in males than in females. But the incidence of carrier, or the prevalence of the carrier state, is not so different. So again, there's sort of unknown features of the epidemiology, which are, to my knowledge, are not still completely explained.
Thanks.
Are there other questions in the room or online? So, Peter, I always describe the study as the oldest step wedge trial, but also the longest running. It's a shame that I think what you're telling us is it's unlikely ever to publish its findings after all these decades.
Yeah. Well, it may not publish its findings with respect to the step wedge, but I hope it will, well, on the next slide, derive something from a longitudinal comparison, but we have to persuade funders of that importance. I think it's fair to say that there were suggestions for using this sort of phased introduction of an intervention in a sort of what would now be called a step wedge way, which I was certainly aware of some discussions in a meeting that I attended at WHO on introducing a malaria intervention in Zambia in a sort of phased way in this. So it wasn't called a step wedge, but and it was, I don't think it was ever published, but but as I say, it was the first one to be called a step wedge, but there may have been other phased introductions before this.
Well, I think you're being unduly modest, but I would say also, irrespective of the publication of the step wedge findings, this study has had a massive legacy, as I'm sure you can see just from the people in this room and the interest. So thank you once again, Peter Smith.
Thank you.
So the next part of the programme is to go back to the earlier talk that we missed in order to get to our tea in time, which is it Brian Blett, who's I hope waiting online, ready to
yes, I'm here.
Share his slides. I can see some slides. That's
can you hear me?
We can hear you.
Great.
So in your own time, Brian, please go ahead.
Yeah, thanks. I appreciate everyone sticking around. I suppose it's a bit anticlimactic having a rapid talk after the invited keynote, especially when it's someone as esteemed as Peter. I kind of feel like I'm performing after Adele at the Grammys, but I'll do my best to keep this short and sweet. So today I'm going to be giving a talk on assessing heterogeneous treatment effects in cluster randomized trials, particularly when you have missing effect modifier data. This is joint work with Scott Halpern and Michael Harhe at Penn, as well as Fan Lee at Yale. So the background for this talk, basically we're going to be focusing on this heterogeneous treatment effect scenario where this is more of a pre-specified HTE type scenario. So in some kind of pre-specified analysis, people plan to look at whether their treatment effect varies across some kind of baseline covariate that they measure. And of course, missing data in all sorts of problems introduces issues. But here, when the modifiers themselves are missing, there are somewhat unique issues that arise. For example, once you specify a certain outcome model that, if you are assessing heterogeneity, might be somewhat complex with respect to the treatment and modifiers. It's not exactly obvious what imputation model to use if you want to use an imputation method, because it has to be something that in some way is going to be compatible with the outcome model choice. So this has been looked at a lot in the observational study setting, as well as in individually randomized trials. But as far as we could tell, we didn't see a lot of work on this problem in cluster randomized trial settings. So the general goal of this work, we wanted to identify imputation methods that were somewhat off the shelf and easy to be used by practitioners for this problem, kind of looking at previous papers on missing outcomes in CRTs, as well as this missing modifier problem that's been studied in individually randomized trials. And then we basically just compared the performance of these methods under various data generating mechanisms in some simulation studies and in some real data. And kind of as a secondary goal, wanted to investigate the impact of this model compatibility problem, kind of trying to assess kind of the degree to which the imputation model is compatible with the outcome model and how that affects downstream parameter estimation. And then finally provide some recommendations on which of these kind of off-the-shelf methods should be used in practice. So the methods that we have for comparison for this paper, we have a complete case analysis, a single imputation, a multiple imputation, and then 2 multi-level multiple imputation procedures. One which is kind of a more frequentist type option, and another which is a bit more of a Bayesian flavor. So just to delve into that a little bit more, so the one that's kind of we refer to as MMI throughout these slides is kind of the more frequentist one. This is sometimes called approximate imputation, improper imputation. Basically what we mean here is that we are going to fit a model for the missing modifier that accounts for the intra-cluster correlation in some way. Let's say it is a logistic mixed effects model for a binary missing modifier. And then we're going to use imputations from that model, say using the EBLUPs, the empirical best linear unbiased predictors. And then we will do that multiple times and combine results across the imputations using, the Rubin rules or a standard procedure. And then the method that we're referring to as Bayesian MMI is, like I said, kind of a bit more Bayesian flavor, perhaps not fully Bayesian, but implementing this inside of a Gibbs sampler such that we're kind of iterating between the parameter estimation of the imputation model and the outcome model to help account for uncertainty in the outcome imputation model estimation. So we evaluated these in a couple simulation studies. In particular for this talk, I'm just going to focus on this first scenario. So we have either 20, 50, or 100 clusters in our design, a 1-to-1 allocation randomized binary treatment. We simulated just one binary effect modifier to keep things simple with an intra-class correlation of 0.1. We have a standard Norberg covariate. We have an outcome model with a fairly complex generation such that there is treatment effect heterogeneity across the level M. And we have kind of up to 3-way interactions, including this extraneous covariate, and then also some intra-cluster correlation in the outcome as well. And then we introduce our missingness problem of our modifier M as a function of X and Y. This is a little bit, of course, not standard for the trial setting where, Y comes temporally after M, but essentially this is just trying to simulate a backdoor path between Y and the missingness of M. You could imagine that it's through some kind of unobserved covariate, for example. And the estimates of interest, primarily an interaction coefficient in the implied marginal model from these generating mechanisms where you integrate out the covariate X, or likewise an average treatment effect estimate. And then within the methods that I talked about earlier, we had complete case analysis plus 4 imputation methods. Within each of the imputation methods, we considered 5 possible model specifications for the imputation model. And so essentially, since we have this binary modifier, we used a logistic mixed model specification. And then we kind of scaled these from less compatible with the true outcome model to more compatible with the true outcome model. And this is primarily based on the interaction terms. So you can imagine if the outcome model has many interaction terms between A, X, and M, that the implied model for the missing modifier likewise should have comparable interaction terms based on kind of the implied correlations in the data. And we have this kind of ranging from less to more compatible because even the model with kind of these full 3-way interactions at the bottom of the page is not going to be fully compatible with the outcome model in the sense that there really is not a joint distribution of the outcome and modifier such that the conditional distribution of the outcome would be normal and the conditional distribution of the modifier would be logistic, but it's, mostly compatible in terms of the interaction terms. And then we present some results from this study, first looking at bias and coverage metrics. So moving from left to right in these panels, we're going from single imputation, multiple imputation, multi-level multiple imputation, finally that Bayesian MMI procedure I discussed. And then the colors within each of the panels represent different model specifications, and then the red color is always just complete case analysis. And basically the findings of the results are that, Of course, accounting for these intra-cluster correlations is really important. So MMI and BMMI do much better than single imputation or multiple imputation. In terms of coverage, we actually see kind of a big jump from Bayesian MMI over MMI to get really nominal coverage results for the most correctly specified modifier model. And we think this is because, kind of like I said, of that iteration between the estimation of the model components accounting for some level of uncertainty that's happening here. Likewise, of course, the more correctly specified your model is, the better you do, and with sometimes quite dramatic differences. We also looked at MSE and type 1 error metrics. So MSE, there really actually was a kind of a surprising lack of difference between MI, MMI, and BMMI on that metric, although it did depend a little bit on the model specification. And then the type 1 error, of course, is kind of just a reflection of the coverage results showing that BMMI had the best performance. So just to quickly conclude, we also ran a second simulation study and application that were a bit more complex. They found very similar results overall. So there's kind of two key things to take away. The first is that you should account for the intra-cluster correlations. So MMI and BMMI were superior to the other methods overall. And then the second thing is to think really hard about the imputation model specification, which clearly had a big difference in the simulation results. I didn't show the second simulation study, but in that one, we found that poor imputation model choices could actually be much worse than complete case analysis to kind of a staggering degree. So you should be really careful when using these imputation methods in practice, especially just, if you're specifying an outcome model that you think is true with all these interaction terms, using an imputation model with only main effects, which to be honest is, the default for many imputation softwares, if you don't start to play with the options, can actually be quite poor and make you end up doing much worse than complete case analysis. Similar results for the ATE estimand, although it was a bit milder than for this interaction estimand. And then in future work, we can consider different ways to look at this problem. In the IRT setting, people have thought about, really deriving fully compatible approaches that kind of derive a Bayesian sampler that is going to exactly be compatible with your assumed outcome model. We found pretty good performance for BMMI without doing that, but there probably are settings where that will have a nice jump in performance as well. And then also considering some non-parametric imputation models that can sidestep these compatibility issues might be good practice. And that's kind of the next area we plan to explore. All right, thanks. I'm happy to answer any questions. And also feel free to use this QR code link with your camera on your phone if you want a direct link to the archive paper. Thanks.
Thank you very much, Brian, for a brilliant presentation. Are there any questions in the room? Brian, you mentioned non-parametric imputation, which I don't know if you started to explain that and I missed it. Can you just say a little bit more about what that might involve?
Sure. So that's kind of our next phase that we're working on now. But essentially what we're thinking of is kind of the fact that, like I said, they're really, these are all kind of very just approximate imputation methods. Once we start specifying a logistic mixed model for the modifier here, we know that that model is probably not going to be compatible with the outcome model and kind of what that implies. So what we're thinking of more so is perhaps a procedure like Bayesian additive regression trees or another non-parametric imputation procedure that's going to still provide imputations in a way that accounts for intra-cluster correlation, maybe through random effects, but also sidesteps the fact that, there's not going to be a right joint likelihood from the outcome and modifier. I can't hear anything on my end. I'm going to assume there's no further questions, but
can you hear us, Brian?
Oh, now I can. Yes.
Okay, I'm going to repeat. We'll repeat the question for you.
Oh no. Okay, I was wondering why there was dead silence for 20 seconds.
I was just asking, the single level multiple imputation you did you adjust for clusters as fixed effects? Because I've seen papers suggesting that as an alternative to multi-level modeling.
Yeah, we actually did not do that, but I think that is a good idea for our next step, because I have seen that in a couple papers where sometimes it performs better than I think, and sometimes I guess it doesn't quite meet the bar, but it would be interesting to see in this setting how it performs.
I've got a follow-up question. This is Andrew Forbes from Monash University. Thanks for a really nice presentation. Just following up from Jenny's question, did you look at any sort of the fully conditional specification or sort of chained equations? Can't recall how many variables had missingness in there, but doing that by treatment group really takes into account all the interactions that could possibly occur.
Yeah, that was a direction that we wanted to pursue. We kind of, as we were writing this paper, we started with one missing effect modifier, and before we knew it, the paper was like 16 pages, and we kind of decided to push the brakes a little bit. But kind of another direction we were thinking of is maybe having a few missing modifiers and a missing outcome, and thinking about that fully conditional specification approach that some of the people here, I think, have developed for IRTs and other settings, and kind of thinking about it in the cluster randomized setting and whether any adjustments need to be made is a really good next step. Yeah.
Thank you, Brian. So can we thank you once again in the room? Last but definitely not least. So we have almost come to the end, ladies and gents. Chris, I don't know if the thank yous are loaded up as a part of this presentation. Oh, there we are. Yeah, they are. Perfect. So just to say a few things to close, it's been an absolute pleasure for me and Beth to present this meeting on behalf of the international group of researchers who convene this meeting every year. And thank you to all the speakers who've made it really so wonderful. It's fantastic to be back to face-to-face meetings. It's really wonderful to see old friends, but also really wonderful to see people coming from all corners of the globe, and to see new researchers, PhD students and others taking up the mantle of studying cluster trials and step wedge trials, which reassures me that the topic is continuing to grow in interest, really. So I want to thank everyone who's been involved. A few particular thank yous. Some of the people, as I mentioned, part of the international group who convened the meeting: Sandra Eldridge, Bruno Giraudeau, Agnes Kai, Carla Hemming, and Clémence Lerat and John Bradley. Jenny Thompson, Michael Grayling, Andrew Kopas. Michael and Andrew also helped us with some reviewing, as some of that international group did. Thank you very much. Thank you also to all the chairs. I didn't mention there that all of the chairs, Andrew Forbes and Liz Turner also chaired. Thank you very much to all the speakers and chairs. Lots of people from our group at QMUL helped make this possible. And the 4 people in particular who have been on site here both days, working very hard and shouldering most of the burden of organising the conferences: Sarah Ghazi, Jeff Franklin, Rima Priyadarshini, and Olivier Quentin. And Beth has a small token of our thanks to give to them today, if we give them a round of applause for all of their help. And we've had massive help from the Whitechapel Gallery, Emily, Sam and Nick. And I haven't mentioned on this slide the 2 Chris's, Chris Peltier and Chris Smith, who've been incredibly patient with us, incredibly kind and helpful all day with our audiovisual problems and issues. Thank you so much to everyone at Whitechapel, including the 2 Chris's. From me personally, thank you particularly to my mentor and former boss, Sandra Eldridge, who has always been and continues to be the driving force behind these meetings. And as I say, thank you to all of you who've participated and taken part. Thank you.